I'm going to give everyone just a few minutes to log on, and then we'll go ahead and start. Well, good morning, good afternoon, good evening, wherever you're tuning in from. Thanks for joining us for today's webinar. I am super excited to introduce our host. First, I'd like to give a brief overview of our organization and what it is that we do. And I ask that if you have a moment to take the time during or after this presentation to make a small donation to Autism Health. We are 100% volunteer-based, and we depend on donations from, our supporters to keep the doors open and to keep, our monthly webinars going, our annual conference, and all our different events that we're going to be hosting. And next month, soon, one of our board members, Krista Bourne, is going to be hosting our first parent meeting, so we can get together as parents and we can ask each other's questions and get some community interaction going. So what is Autism Health? We are a 501c3 nonprofit organization dedicated to funding scholarships and providing resources for families that are impacted by autism spectrum disorder and also other neurological conditions. So today's speaker is Robert Miller, and he has been a wonderful supporter of Autism Health for almost 3 years now. Even before we became an organization, he supported our conference and has always been a speaker. So Bob is a traditional naturopath specializing in the field of genetic-specific nutrition. He earned his naturopathic degree from Trinity School of Natural Health and is a board certified through the ANMA. In 1993, he opened the Tree of Life practice, and he has served as a traditional naturopath for 25 years. For the past several years, he has been engaging exclusively with nutritional genetic variants and related research, specializing in nutritional support for those with autism and chronic conditions. So welcome, Robert Miller. We are super excited to have you. A little bit about us. I did discuss a little bit about what it is that we do. We are mainly focused on, funding research and education for families impacted by autism. And we do this through many different pillars. And most of all, we do it through our engagement, our community, our compassion for learning, and we empower families to be advocates themselves, to be the biggest advocates for their children, for professionals to advocate for their patients, and for caregivers. So who are we? My husband and I founded Autism Health, and we initially did that because our son, 17 years ago, was diagnosed with autism. And with that, we were able to turn him around with biomedical intervention. And because of that, I wanted to be able to assist families and being able to do the same for their own loved ones. Our board of directors is Melanie Dokis is our treasurer, Krista Bourne, our secretary, Mia Romero, our directors. Board members are Patricia Marone, Jesselyn Castellini, Amy Schaffert, and Jackie Christensen. Our advisory board, we have Dr. Joshua Burka, Joseph Sliskovich, who's our attorney, Dr. James Lyons-Wheeler, Dr. Richard Bartlett, and Dr. Jerry Cartsinell. So, a call to action, we truly believe that everyone can make a difference no matter what size that contribution is. So, like I said before, if you could just take the time to make even a small donation, or if you would consider making a reoccurring monthly donation, no matter what that amount is, it does add up and it does make a huge difference. And we are at this time 100% volunteer based. So we thank you for, we want to thank our community and our supporters because if it wasn't for you, we wouldn't be able to continue our mission. Our mission is to provide as much support for families moving forward. We do have tickets on sale for the Autism Health Summit. So you can go to autismhealth.com or ahsconference.com, either one. And you can purchase your ticket. Tickets do go up January 1st. For the month of October, you can get $25 off your ticket with Spooky25 discount code. But right now they are discounted $100. So that amount will go up after January 1st. And we have some great speakers, great sponsors, and we look forward to having you all there. So right now I'm going to go ahead and I'm going to turn this over to our speaker of the day, Robert Miller.
Well, thank you, Tracy. And again, thank you for all that hard work you do. I know you're all doing it all volunteer and you're doing it out of a heart of kindness for all these people that are struggling. So hats off to you for doing that and your whole organization. What we're going to be talking about today is how the neuroinflammation of autism occurs because of environmental and genetic factors. There's an old saying that says, genetics loads the gun, environment pulls the trigger. So there's probably many reasons why we're seeing such a rise in autism. But we all know, you've all heard this statistic probably 50 times. Autism used to be 1 out of 1,000, now it's 1 out of 33, and the fact those numbers are changing as we speak. So the question becomes, well, why is that happening? Well, I believe one of the primary things is the environmental factors that we weren't exposed to in the past. One of my favorite jokes is back in 1954, when I was born, Earth was a different planet. We didn't have glyphosate. We didn't have growth hormones given to the animals. We didn't have microplastics. We didn't process our foods as much. Just on and on, all the things that have changed that are now creating an inflammatory condition that's impacting us and our children the most. And not only our children, but if you look at dementia and the memory loss in the elderly people, it appears as though what's happening to our children with autism is now happening to us as we age with memory loss. So there's something going on here. Now the question becomes, well, we're all living in this same toxic soup that at the same time, why are some people more impacted than others? And that's where the genetics comes into play. Some people are more genetically predispositioned to overreact to the environmental factors. And aside from that, I think we've all noticed that the level of agitation and irritation in people just seems to be rising. And also, aside from autism, the ADD, the ADHD, when I speak to teachers that have taught just 10 years, they'll say, my goodness, the amount of kids now that can't pay attention, they're not focused. So autism is like the ultimate of this, but just the agitation that everyone's feeling, the ADD, I believe it's all part of the same part and parcel of what's happening to us. So we want to be talking about the environmental factors and the genetic factors. But first, a little bit of genetics 101, because people get confused on this. So we're going to try to put it in simple terms. So when everyone is conceived, when the father's sperm burrows into the mother's egg, your DNA is made. Now, what an absolute miracle we are. We eat fats, carbohydrates, proteins, we drink water, we breathe air, we're exposed to sunlight, and somehow everything gets made. I mean, when you really step back and think about that for a second, that's pretty darn incredible that that's the way it works. Now, the way that works is your body makes what are called enzymes. And enzymes take one substance, combine it with something else, and make something new. And then another enzyme comes along, does the same thing. And that's how everything gets made. Your hair, your skin, your nails, all of us on this webinar right now, our enzymes are working to beat the band, to make our hair, skin, nails, turn everything into energy, create new cells. I mean, it's truly astonishing. And I don't think we can even begin to fully grasp the complexity of it all. But it's the enzymes that do the work. Well, where do the enzymes come from? The enzymes come from your DNA. So your DNA is the instructions on how to make the enzymes. So as you probably all know, if you have a child who's a male, uh, the father donated the Y enzyme and they're XY. If it's a female, it's XX. So there's two pieces of information that are the instructions on how to make the enzymes. And I'm sure you've seen DNA. It looks like that twisted pair, the double helix. And in there lies the instructions on how to make the enzymes. Well, what can happen is we can get what are called SNPs, single nucleotide polymorphisms. And when you get a SNP, it isn't, the end of the world. I mean, they're very, very common, but it impacts the ability of the enzyme to do its job. So we get two pieces of data for every enzyme, one from mother, one from father. And if one person gives that SNP, then that means that the enzyme is going to work, but it may only be 70 to 80% as effective when called upon. If both parents give that SNP on the same enzyme, it might be 30 to 40% effective. And then interestingly, there's a couple of SNPs that we're going to talk about today that they actually make the enzyme go faster. So if you've got an enzyme that transports your fats, transports your folate, makes your antioxidant, it's slower, you're not going to detox as quickly. We're also going to talk about some enzymes that make inflammation, that they're there for a part of your immune system, but if they're overactive, we have a problem. So a simple way to understand this that people seem to gravitate towards, think of cars. An 8-cylinder car, that's when both parents give the right data. 6-cylinder car, one parent gives misinformation. 4-cylinder car, both parents give misinformation. Now, does a 4-cylinder car look the same, drive the same? Sure. But if you're out on the highway and you need to go up and down some mountains while you're pulling a trailer behind you, probably not a good idea. Or if you're, going down the highway and you need to pass somebody, that 4-cylinder is not going to be as effective as a 6 or 8. And then we get turbocharged where you tap the accelerator a little bit and kaboom, off you go. So overactive, normal, slightly underactive, relatively underactive. That's what we're going to talk about with the genetics. So I hope that makes some sense. So I'm going to do a screen share here with you folks, and we're going to start looking at what we're talking about here.
So while you're doing that, I just want to let everyone know that I forgot to tell you, if you have any questions during this talk at all, please put them in the Q&A, not the comments section. So at the end, we will go through the Q&A. So the Q&A should be down at the bottom of your screen. It says Q&A and it's got a little question mark. And you can put your question in there. And then what we will do is we will go ahead and answer everyone's questions afterwards. And then if there are any follow-up questions, if you forget something, you can email us at info@autismhealth.com and Robert will answer those questions for you. We will get back to you as soon as possible. Do your best to jot down all your Q&A during this talk. You don't have to wait till the end. And I'm going to turn this back over to you, Bob.
Okay. All right. I think you see the slides, correct? Are we seeing the
Yes,
slides?
we can see it. I can see it.
So the topic is the epigenetic and genetic factors leading to increased, and I'm sure you're looking at this as like, Bob, what is that? I'll explain that. But I think most of you know what histamine is, and glutamate, I'll explain those. And again, you just want to say this is educational, informational. We're not diagnosing or treating any disease. This does not come from me alone. I just want to give thanks to my team. This is Matthew Miller. Yes, this is my son. He has his master's in pharmacogenomics. Dr. Ann Kelly, MD, functional medicine certified pediatrician. Dr. Harold Landis, fellow in integrated medicine. And Yvonne Lucchese, she's the executive director here at Functional Genomic Analysis. But despite all of that work, helps with the research as well and wears many hats. And we're thankful to all of these folks who make it possible. Now, what we're going to be talking about today is there was a study called the Pearl study where we looked at 36 autistic children. And there was many, many, many things looked at. I mean, there was many things measured. They were put on a diet. They were given a multivitamin, and nice improvement was seen. But I'm just going to be talking about my portion of it, and that is the genetics. So we donated our genetic test. By the way, we have our own genetic test called functional genomic analysis. We decided what SNPs go in it, and I'll talk about that a little bit at the end. So we donated that to these 36 kids, and we started analyzing what was happening with them. Now, probably you all know this. I just put this slide in that there is no debate anymore that what we have with autism is dysregulated neuro being the brain inflammation. There's nobody who's going to argue that there's not neuroinflammation going on. And then here's another paper, the role of neuroinflammation in autism spectrum disorder and the emergence of the brain histamine system. So there's no debate here that we've got inflammation going on. Now, some of the latest research is looking at something called NLRP3, making an inflammasome. So I'm going to explain what this is in a minute, but I just wanted to show you peer-reviewed studies. These are PubMed. This isn't just somebody blogging on the internet. There's 3 of them here. If you would put that into a search engine, this whole study would show up. I'm just showing you the title. So they're saying there's a mitochondria, that's the energy inside the cell, this loop in autism. Here's another paper. Multiple inflammasome complexes are activated in autism spectrum disorder. And here's another one, abnormal mitochondria and LRP inflammasome crosstalk. So again, if you want to read these articles, just type that in and the whole article will pop up and you can read it. So we just put it here to say that inflammasomes are a large player in autism. And here we just put a little more information, but the bottom line says these results provide the first evidence of a pathological bidirectional interaction between mitochondria, that's what makes the energy inside the cell, and the NLRP3 inflammasome in autism spectrum disorder. So there's now scientific evidence that this inflammasome is behind this. Now, what's an inflammasome? So here we go. So what happens is when we get what are called PAMPs, that's pathogens. That could be mold, that could be Lyme disease, that could be a virus. DAMPs, that's when it's called damaged molecular proteins, when a cell becomes damaged. They go through a process here, and I believe I have the drawing tool. Cool. Nice. So here's your PAMPs and your DAMPs, and then something called toll-like receptors, and then they stimulate something called NF-kappa B, and I'm going to tell you what that is. Then it stimulates that NLRP3. And then it creates what are called gasdermins, okay, that then makes what are called cytokines. It's not really important what they are, but they're very inflammatory. And they start punching holes in your cell membrane. So every cell inside the body has what's called a phospholipid bilayer. Every cell has that around it. And we start punching holes, and then you start getting disruption of the neurotransmitters. So again, we have step 1, priming, PAMPs, DAMPs, turning on the gasdermins, punching a hole in the cell membrane. That, in very simple terms, is pyroptosis. Now, it says here the inflammasome pathway is a critical part of your innate immune system. So if we didn't have this, we'd die of infection. So this isn't all bad, but the problem is when it gets out of control. So it starts with this caspase-1, then as I said, the inflammatory 1-beta and the interleukin-18, and then pyroptotic cell death by the gasdermins. All right, so what are gasdermins? Interesting, this isn't a term we came up with. They're called executioners of pyroptosis, the death of the cell, programmed cell death. So what it does, it forms a membrane pore in response to inflammatory signals, leading to cell swelling, lysis, and the release of pro-inflammatory cytokines. We said these before. Cytokines are inflammatory. Now, the pyroptosis, that's what we're talking about, where the cell gets damaged. Again, peer-reviewed study. Evidence suggests that the induction of pyroptosis from this NLRP3 inflammasome is involved in psychiatric disorders, depression, stress-related issues, schizophrenia, autism spectrum disorders, and neurodegenerative diseases. Again, if you'd like to read the article, just type that into Google, those exact words, and the paper will come up for you. Now, this is the hypothesis that we've put together for what causes autism. And this is what we studied in those 36 children. And I believe it's going to prove to be quite helpful. So once again, we've got a cell membrane. It's called the phospholipid bilayer. As you know, we're made up of trillions and trillions of cells. I mean, again, what an absolute miracle we are. Those cells have what is called a cell membrane around them. So we want it to be nice and healthy. And we're going to show you why in some of these children, they get off to a bad start by not making this healthy. Then here comes your environmental toxins, other internal factors. Remember I told you that you can have turbocharged enzymes and you can have some that are weak. So if you've got some turbos and some underactives, it stimulates an enzyme called NF-kappa B, and don't worry about the name of it. That stands for nuclear transaction factor, nthroid. And then that stimulates the inflammasomes, and then that starts punching a hole in the cell membranes. And your neurotransmitters, glutamate and dopamine, get dysregulated. Well, there's your autism, folks. Then through this guy, we make something called hydroxyl radicals, we'll get into later. That creates what's called lipid peroxidation. We start poking holes in the cell membrane. Now, it's interesting, we use this model for autism, but when I spoke at a cardiovascular event, I used this to show how cardiovascular events occur. And if we were doing one on Alzheimer's and dementia, it'd be the same thing. So I'm going to show you then why this is now happening at a more alarming rate. But first, let's look at how we build that phospholipid bilayer. So again, this drawing right here represents your phospholipid bilayer. Let me get my drawing tool here. So this is your phospholipid bilayer. Okay. Now we need something called phosphatidylcholine to build that cell membrane. Now, remember I told you genetics is the instructions on how to make the enzymes. So there's an enzyme called PEMT that takes choline, turns it into phosphatidylcholine, builds the cell membrane. So what do you think happens if you have genetic SNPs on this enzyme right here? Well, you're not off to a good start. Then your dietary fats, like fish oils, just the foods we eat, there's an enzyme called FADS1, FADS2, and ELOVL2, and that makes something called DHA that also builds your cell membranes. So what happens if you don't have enough phosphatidylcholine and DHA? You're not going to make this very well. Now, inside your cell membrane, you have something called ubiquinol, that's your CoQ10, vitamin E, vitamin K, vitamin A, and vitamin D, that actually sits in the cell membrane. And what that does is that protects the cell membrane from being damaged. And then we're going to get into it a little bit later. You can have genetic mutations on these enzymes that they're weak. You can have some trouble turning beta carotene into vitamin A. You can have a little trouble with vitamin D. So if you don't now have the protection inside the cell, when oxidative stress comes along, this guy is going to be damaged even further. So two pieces to this. Build it nice and strong, protect it. Build and protect. I hope everybody's with me on that. Okay. So now we're going to look at, well, what happened to these kids in the study. Now, when you look at genetics, there's what's called RS numbers. And, you don't have to get too confused on this, but this is just how you identify the gene. These three right here are the ones where there's literature on when you got a SNP, they don't do their job as well. So remember, dietary choline through the PMT makes phosphatidylcholine. So out of the 36, 50% of them had a single mutation, one SNP from one parent. 39% had both parents giving weakness. So 6-cylinder car, 4-cylinder car. The other one, 61% had one, 19% had two. The third one, 50 and 14. So bottom line here, all of them, every one of the 36, had at least one heterozygous, that means from one parent, or homozygous from both parents. Every one of them had weakness in building the cell membrane. Isn't that absolutely fascinating? Okay. Right, now we're going to look at the FADS1. And I'm not going to read these numbers. If you want to watch the video later, if you want to pause it or something, if you want to write these down, but these are the RS numbers. And 50% had at least one from one parent or from both parents on FADS1, and that's where you make your DHA. Your FADS2, same thing, 50% had a mutation. And the final step, 67% had trouble with this. So in my opinion, if you're trying to help an autistic child improve their health, step number one might be, how are we building that cell membrane? Is that cell membrane nice and strong? Because if it's not, we're going to be in trouble. So I hope I'm saying this in a way that makes some sense. Now we have to go to the protection of the cell membrane. So remember, I told you that CoQ10 is inside the cell, and that will become oxidized and become CoQ10 oxidized. Well, there's three enzymes here that are involved: NQO1, NRF2, and KEAP1. In my opinion, NQO1 might be one of the most important enzymes we want to look at in autism. I'm going to show you how it plays so many roles, but it's part of what takes your oxidized glutathione, in other words, not glutathione, oxidized CoQ10, and turn it back into what's called reduced so it can protect. If this guy's not here, the cell gets broken down more easily. So look at this, 44% had a mutation on NQO1 that it doesn't. Take the oxidized to the reduced as well. This gets a little complicated. This will probably be one of more of the difficult things. There's an enzyme called NRF2, okay, and KEAP1 that control this, and 61% of them had what's called a gain of function on KEAP1 that suppresses the NRF2 that helps the NQO1 do its job. And this plays many, many other important roles inside the body. So again, if you're getting a little lost in the biochemistry, don't worry. All we're saying is that these kids may not build their cell membrane as strong, then they have difficulty protecting it. And I know in a previous webinar, you had Dr. Goodenow on where he talked about the plasmalogens. So what they're doing there is they're trying to jump in and help rebuild the cell membrane. All right, now let's look at the vitamin A. So as you may know, beta carotene from your colorful fruits and vegetables turns into vitamin A. And you can see here on one of the enzymes, 72% had a heterozygous or homozygous. On the other one, 44%. So they have trouble getting the vitamin A in there. And then the same will say with vitamin D. 72% had difficulty getting vitamin D into the cell membrane. So that's why it's so important to look at the genetics and see where the weakness is. Are they having difficulty making the cell membrane? Or maybe they make the cell membrane just fine, but they can't protect it from the onslaughts. And I'm going to show you those coming up here. Now, here is why vitamin D is so important. Again, here's your cell membrane. I'll draw one here. Here's your cell membrane. And there's something called an enzyme called SLC40A1 that takes iron, this is the symbol for iron, into the bloodstream. Okay. If it doesn't happen and stays inside the cell, it creates what are called hydroxyl radicals and lipid peroxidation and starts damaging the cell membrane. So vitamin D suppresses the hepcidin that suppresses the SLC40A1. Now that's a little bit like Abbott and Costello, who's on first. I get it. But the bottom line is, if we don't have enough vitamin D, we're not going to keep that, like iron's going to stay inside the cell and start doing damage rather than being utilized. Okay. I hope that makes sense. So vitamin D If you want the simple version, Cliff Notes, vitamin D reduces the chance of the cell membrane being damaged. You don't have to stress over the SLC48-1 and the hepcidin. I mean, for some people that are really into biochemistry, they like all that, and it really doesn't much matter. Bottom line, vitamin D protects the cell from being damaged, if we want the simple terms. All right, now here's the crux of the matter. We are being exposed to environmental factors that we weren't exposed to before. That's why I said, one of my jokes is, I was born on a different planet in 1954. So we did not have mycotoxins being as strong. We didn't have microplastics. We didn't have glyphosate. Yes, we got vaccinations, but not 72 of them. We didn't have cell phones. We didn't have high fructose corn syrup. That only came about in the late 60s. Then if you get any of these conditions, Lyme, hypoglycemia, stress, oxalates, we'll talk about those a little bit later, then these things start stimulating enzymes that are inflammatory. So remember I said there's some turbocharged. Well, if an enzyme called TNFA or NF-kappa B or these interleukins or overabsorption of iron and on down through here, if they are overactive, it's going to create more inflammation. Then there's enzymes that are anti-inflammatory. Now, if some of these are weak, we've created the perfect storm. So environmental factors, stimulating genes that are there to protect us, but they can be overactive, they can be turbo, and then the guys that protect us can be underactive. So what happens when we have that proverbial perfect storm? I'm sure you've heard of tsunamis. They don't occur by one event. They have multiple factors coming together. So what happens here, my friends? Here's what happens when these conditions occur. An enzyme called tumor necrosis factor alpha, has nothing to do with tumors, stimulates something called NF-kappa B. Then this is your inflammasomes right here. If you remember that drawing I showed you, that NF-kappa B is the binding of NLRP3 inflammasomes. Then through this pathway, remember I said interleukin 18, interleukin 1 beta. So interleukin 18 makes histamine, mast cells, can lead to schizophrenia and bipolar. Now, what's interesting, this feeds back in a feedback loop, and we have a feedback loop going on. Over here, we make excess glutamate, and glutamate is what makes you intelligent, highly motivated go-getter, and that's why some of these children are absolutely geniuses, brilliant. They're not stupid. They're very, very smart, but their glutamate is so high they can't focus, and they're just they're struggling. Well, then look what happens here. That glutamate comes back through this enzyme and creates another feedback loop. And this is what we're hypothesizing is occurring. Now, don't want to make this any more complicated than it is, but we need to get this into it. The body's absolutely amazing. We have what are called sirtuins that we're going to talk about a little bit later. SIRT1 inhibits NF-kappa B. SIRT2 inhibits NLRP3. And SIRT3 helps take glutamate, that excitatory neurotransmitter, and turn it into something that's helpful inside the body. Well, guess what, folks? We can have genetic mutations on the sirtuins, that they don't do their job as well. Now, hope you're sticking with me. NAD, I don't know if any of you heard of that, nicotide adenosine dinucleotide, is the fuel for the SIRTs to do their job. And I'm going to show you later why you can underproduce this, or you can actually use this through what's called CD38 to actually stimulate NLRP3. We'll have slides on that later. But what we're saying here is this NAD is used by the sirtuins to hold back inflammation, and under the wrong conditions, it will be used to create inflammation. So that's why this is so complex. I mean, we don't have here's what causes autism, and I believe this is why it's been so difficult, because you can see there's just so many factors impacting it. Now, I want to talk about NF-kappa B, and again, that's This guy right here, as you remember in my first slide, that's the guy that kicks it off. This is where all the trouble begins. This is the troublemaker. Now, NF-kappa B is what's called a transcription factor. Now, if you didn't have NF-kappa B working, we wouldn't be here because it kills virus and bacteria. So inside your cell, you have something called the cytoplasm, where it hangs out. And then when it's released, it goes into the nucleus and it turns on hundreds of genes related to inflammation. These are all inflammatory. Now, this isn't just autism, rheumatoid arthritis, Alzheimer's, Parkinson's, cardiovascular disease, cancer. All of those happen when this is running too quickly. So here you can see, here's NF-kappa B. I'm going to draw. So one analogy that people are saying makes a lot of sense is that think of this as firemen. They're sitting in the fire station. They're playing cards, taking a nap, watching television, chatting. The alarm goes off. They jump into action and go fight the fire. So here's NF-kappa B in the cytoplasm, just, do-doop, hanging out. When they're released by this guy, so here you got HIV, Epstein-Barr, even COVID-19, this guy holds him back. And he says, don't get too excited, guys. Keep hanging out in the station. When this guy is suppressed, he releases NF-kappa B to go into the cytoplasm and stimulate that NLRP3. Now, one of my favorite sayings is, this is a good thing unless it isn't. So if you wouldn't have this guy, you'd die of infection. So when virus or bacteria comes along, by golly, you want this guy. If you got a fire, you want the fireman to show up. But the problem we're having now, my friends, is that this is being activated unnecessarily. And look who's the culprit. But before I do that, this guy holds back NF-kappa B. This guy, IKKB alpha, holds back this guy. Now, what happens is, look at this list. I'm not going to read them, but that's the whole list of environmental factors. Highlights, mold, Lyme disease, aluminum, lead, mercury, nickel, glyphosate, okay? They will stimulate IKK beta that inhibits IKB alpha that inhibits NF-kappa B. Now, again, if this sounds like Abbott and Costello, who's on first, and it's like, oh my God, Bob, that's too hard. Bottom line is, I mean, again, we have people who don't want to nerd out, that want to know all the details. But if you're like, oh my God, I'm so confused, don't worry. These environmental factors cause NF-kappa B to be overactive. That's all you really have to know. All these environmental factors cause NF-kappa B to be overactive and then stimulate all those inflammasomes that we looked at before. So that's relatively easy to understand. The environmental factors cause this to happen. Now, we're all exposed, to the most part, for the same environmental factors. Why are some people okay and some people not? We're going to get into the genetics of how this can be weak to begin with. This can be turbocharged. Tumor necrosis factor can be turbocharged. And remember, I told you that SIRT1 holds this guy back. This can be weak. It needs NAD. This can be weak. We told you about how DHA builds a cell membrane, but it also holds this guy back. It can be weak. And then we make something called hydrogen sulfide that I'm going to talk about in a little bit. That holds it back. That can be weak. And we also make something called bilirubin, and that can be weak. So if this is a 3D chess game played underwater, I've never seen one. I mean, this is, as you can see, it's complex. But the bottom line is now, by looking at the genetics, by looking at the labs, you can see where you need to jump in. So you could see 20 autistic kids in a row. For one of them, it might be the SIRT1's too weak. For another one, they may not be making enough NAD. For another one, they may not be making the DHA. For another one, the TNFA might be overactive. This might be underactive. We may have keep one being too strong that we don't make enough bilirubin. All of those things together. And, we talk to a lot of folks with their autistic child, it's usually never one of them. It's usually multiple. But I don't know mathematically how many different combinations there can be, but you can see that this would be a lot of combinations that would cause this. There isn't just one thing. So that's why people get so frustrated. Somebody says, well, take fish oils. Well, if you have trouble here, the fish oils won't work. So somebody else might say, well, take NAD. Well, if NAD is being used improperly, it'll make you worse. So there's just so many factors here that have to be compounded together. Now, let's look at what happened in our study. Remember, IKB alpha holds back NF-kappa B. 75% of them had weakness on this enzyme. 31% had it from both parents. This is about 12% in the general population. So what that means is, again, if you're getting a little confused, and I get it if you are, but stick with me. Oh, by the way, at the end, I'm going to give a preview of what we're going to be speaking about at the spring conference, and that's leucovorin and acetaminophen. We're going to give you a sneak preview, so stick with me through the whole thing. So this guy holds it back. Well, 75% of them had this guy too weak. So environmental factors comes along, kaboom. The NF-kappa B, 69% had a SNP on this one. So if we look at 696 and this one, 94% had a SNP in at least one of the two. 53% had a SNP in both. In other words, 53% of them had this underactive and this overactive. So look how they're going to be that stimulation for the NLRP3. See how this all coming together, rather complex, but this is a complex situation. Now, tumor necrosis factor also stimulates NF-kappa B, and you can see 42% had a turbocharged TNFA. And then also, as we talked about before, some of them were turbocharged on NF-kappa B. So you can see genetically predisposition for this to be overactive. Now, we already covered this when we talked about the cell membrane, so I won't repeat it, but you need the EPA and the DHA to hold this guy back. And I went through this before, so you saw that in the very beginning. Not only does this build the cell membrane, but this also is needed to hold back NF-kappa B. So if you've got this going on, many times what we suggest is switching to, rather than a fish oil, an algae-based DHA to hold that back. But you got to know what's happening. Now, this one I found particularly fascinating. Okay, so what happens is there's an enzyme called there's a gas called H2S, hydrogen sulfide. Now, some of you might be saying, wait a minute, Bob, isn't that if you're working in the sewer system and you're inundated with that and you breathe it kills you? Yep. Well, what about farmers? If they're in the silo and they get too much silo gas, does that kill them? Yeah. But inside the body, the little bit that we make, this blew us away in the research. Hydrogen sulfide in teeny tiny amounts inside the body, not breathing it, inside the body, suppresses tumor necrosis factor, suppresses NF-kappa B, suppresses NLRP3. These are the ones that make the cytokines, suppresses the gasdermins that does the pyroptosis, and suppresses the keep that holds back the nerve too, all from a gas called hydrogen sulfide. But then additionally, hydrogen sulfide helps all the sirtuins, and the sirtuins help hydrogen sulfide. So what we're finding is that many of the children that are struggling are having trouble making hydrogen sulfide. And that's why sometimes Epsom salt baths are helpful. Tell you what, if any of you that are listening, if you've seen Epsom salt baths are helpful, just put a quick comment in where the questions are. It's like, yeah, Epsom salt baths helped. Because Epsom salt baths will help make that hydrogen sulfide. But we formulated a product called H2S cofactors, and I'm not here to promote products, I'm not pushing them today. But we created a product called H2S cofactors that helps that. Now, how does that get made? Homocysteine, through what's called the CBS enzyme and the CTH enzyme, and a couple of others, makes this hydrogen sulfide. So if we've got genetic mutations, if we've got some 6 cylinders or 4 cylinders here, if we got some 6 cylinders or 4 cylinders here, we're not going to make enough hydrogen sulfide. Now, what's interesting, uh, as you know, the folks that have immigrated here from India, many of them are engineers, doctors, computer programmers. They're very highly educated. They're very intelligent. Now, when they've noticed that they have a much higher amount of autism among their children than they do back in India, just preliminarily, but I'm seeing a lot of these mutations in the people from India that also can make you very intelligent. But then when you come to America and you adopt a more Americanized diet, you know, the Indians, they make a lot of their food fresh with a lot of garlic and spices. So by doing that, they're helping make hydrogen sulfide. My first clients this morning, uh, 3 boys that I see their mother, and her mother has the most amount of mutations I've ever seen in CBS. And she has to take 7 Epsom salt baths a day to survive. 7. So she's in and out of an Epsom salt bath all day. So I talked to him this morning. I said, how's your mother doing? Oh, she's much improved. She's not having to take as many Epsom salt baths because we're helping her make that hydrogen sulfide. Now, there's another piece to this. We need something called heme to make that. So if you've got genetic mutations in your heme cycle, or here, you're not going to make enough hydrogen sulfide. Okay. So this is very important that you make adequate amounts of that, because I'm going to show you every place that this is involved with calming down the neuroinflammation. So in the CBS enzyme, cysteine betaine synthase, there's one enzyme with one RS number that makes hydrogen sulfide in the brain. Look at this, folks. I mean, mind-boggling, absolutely mind-boggling. 81% have a SNP in this enzyme. That's why I put a star here. It's like, OMG. Okay. So then on the CTH enzyme, 28% have a SNP. And then somewhere in here, I summarized how many have both in some of these numbers here. So if you've got CTH and CBS, you're going to have one heck of a time making hydrogen sulfide. Then what I'm going to talk about next is, this is what's called the heme cycle, where we make the heme, and you probably know where I'm going. You can have genetic mutations here that impact the production of the heme. Okay, so now we're going to look at the next thing here. Here is that heme cycle. So glycine, succinyl-CoA go through all these steps to make the heme. Well, you can see here on this ALAD, and I'm going to talk about that later, 72% of them have a SNP. And when you look at the 2 ALADs, 89% have a SNP. In the UROS, 77% have a SNP. So we're not going to get down through here to make that heme. And look what heme does, my friends. This is absolutely astonishing. Heme is not just about making your red blood cells. Phase 1, cytochrome P450 needs it. Electron transport chain needs it. Making nitric oxide needs heme. Suox that turns sulfites into sulfates. Catalase, a major antioxidant. Peroxidase is the antioxidants. All of those are dependent upon heme. And if we've got some genetic SNPs along the way here, this gets disrupted. Now, one of the ways to tell if this is not working very well is I say, do they ever get hangry? In other words, they're agitated, fearful, worried, and this happens to adults as well. And what that means is that porphyrins need to go from this pathway here. They will block the GABA receptor, then you get something to eat, and then you feel better. So for many of these people, intermittent fasting is a disaster, and they need to snack. You need to know if that's happening. Now, here is excess N of kappa B from SIRT1 or NQO1 and NAD weakness. So remember, we told you that SIRT1, and here's a little more detail. SIRT1 takes NAD and slows down NF kappa B by a process called deacetylation. You can have mutations here. Now, remember, I said earlier, there's a dance between hydrogen sulfide and SIRT1. But no matter how your SIRT1 is doing, if it doesn't have fuel, it's not going to work. And your NQO1 controls how your NAD gets recycled, but it's all controlled by NRF2 and KEAP1. So we went over some of this before, that the KEAP1 mutations, but the SIRT1, 31% of them had a weak SIRT1. We talked about this earlier, the NQO1. And then here's the NRF2 that controls all of this. 100% of them had at least a heterozygous or homozygous on NRF2 that controls this. So you can see how this is just accumulating, and why two people can be exposed to the same environment. One person is not affected, the other one is. Now, mycotoxins. This blew us away, folks. Ochratoxin is one of the forms of mycotoxins for mold. In the study, 31 of the 36 were over the upper tolerable. Mind-boggling. Absolutely mind-boggling. Now, these urine tests are very accurate. However, keep in mind that these urine tests only show what's being excreted. Okay. So it's only showing what's excretion. So if you have inability to detox, it's not out of the realm of possibility that you don't show high levels despite the fact that you have it. So I would speculate that more than 31 of the 36 had mycotoxins. Some of them may have been so weak that they weren't able to actually get on. So I hope that makes some sense. So the that's what's happening. So mold appears to be getting stronger. Now, what's the problem with mold? Well, mycotoxins, as you might expect, stimulate the NLRP3. So here they come down through here, stimulate NF kappa B, stimulate NLRP3, and we start punching holes in the cell membranes. Okay. So now we have a real problem here with, the the cell membrane being damaged. Now, the body is pretty darned amazing. So we have the ability to deal with this. I mean, the miracle of the body is just beyond comprehension. But there's a enzyme called UGT1A1 that does a process called glucuronidation. And what it does, it attaches the mycotoxin to your bile, and the bile is what your liver makes, stores in the gallbladder, and that's what makes your bowels move, and excretes it in the stool. And we see many of these children constipated. Well, why is that? Because ochratoxins suppress the enzyme that makes your bile. So this is like a way for these ochratoxins to survive. The ones that killed off the bile are the ones that survive. So now we're getting some more of these. It's like, survival of the fittest. So if an ochratoxin suppressed your bile, it's the one that survives. So ochratoxin suppresses the bile production. Then there's a liver bile pump, and then glucuronidation pulls it out. Something called glutathione conjugation pulls it out. And I'm going to show you why in a lot of these children, they have difficulty here. They can't clear the mycotoxin. So you can see how this just continues to be an issue. So here we go. The CYP7A1 and the ABCB11, that's your liver bile pump, but they're all controlled by NRF2. So, and glucuronidation is what grabs the mycotoxin and puts it into the stool. 75% of them have weakness on glucuronidation. Then we talked about this before, NERV2, 100%. The 61% have a keep one. So the masters that tell these guys how to do their job are weak. And then this is your glutathione conjugation. And again, this is probably a little overwhelming, but what happens over here, we don't have to look at this whole chart, but you can see here that here's your ochratoxin. This is the enzyme that takes it out, excretes it in the stool. Okay. But it's all controlled by NERV2 and KEAP1. So this isn't going to do its job as well. Okay. All right. Then when we look at the enzyme that recycles glutathione, in other words, glutathione is what takes it out. So you'll see here that we've got ochratoxins being excreted in the stools by this enzyme right here. And look at this, 72% of them have a SNP on this guy that it can't do its job as well. But then we also have trouble, I showed you before, taking your oxidized glutathione back to the reduced. And then we also have some trouble making glutathione, but you'll also see that mycotoxins inhibit your body's ability to make glutathione. So a lot of people say, well, let's take some NAC N-acetylcysteine to make glutathione. Well, if you've got NERV2 not pushing this along, or you've got mycotoxins, it never gets there. And therefore, the N-acetylcysteine is not helpful. So you can see how this thing just keeps feeding and feeding upon itself. So now the bile pumps. So remember I told you that CYP7A1 is what makes the bile. Okay. So this guy right here is your bile production, but 67% of them had a SNP on that one. 69% had a heterozygous or homozygous. So in summary, 61% have a SNP. So when you've got weakness here, and then if you've got weakness on the bile pump, so all 36 of them had at least a heterozygous or homozygous on one of these two. And then 61% have a SNP on the CYP. Sorry, that's a typo there. And the ABC11. So 61% of them have trouble on both of these. So in other words, they're not able to get the bile to get the mold out. And this is why many times they have constipation. And then they just don't get that mold out. And then what does the mold do? Well, it just continues to make all this neuroinflammation. So in my opinion, anyone who's got an autistic child really should be doing a mold test on them, but doing mold testing in the home. Now, one of the problems we run into, and I run into this all the time because in our clinic, we just don't see autistic children. We see people that are really ill, and we talk about mold. And the first thing that comes out of their mouth is, well, there's no mold in our house. We don't see anything. And it's like, yeah, I believe you. But mold can be in the carpeting. It can be in the heating ventilating system. It can be in old books. Uh, just because you don't see massive amounts of mold growing on the walls, that doesn't mean you don't have mold. So I would encourage everyone to do something called an ERMI test, ERMI, collect dust, and then see if you have mold. It's one of the biggest challenges we have. And then we have some people who say, well, I don't believe that. I don't believe that mold could be a problem. Well, if you just do a little bit of searching on the internet, plenty of peer-reviewed studies. So as I was just telling somebody the other day, I was talking to an Amish lady who is sick as can be from mold, and she says, but my husband doesn't believe that mold can be a problem. And my response was, well, belief is religious type things. You don't get to believe whether mold creates neuroinflammation. It just does. So I don't know why we get into this argument of I don't believe it. You know, it's like To me, that's like saying, I don't believe in gravity. Well, step off a roof and let me know what happens. Mycotoxins cause neuroinflammation. This isn't something whether you decide whether you believe it or not, it just does. And that's one of the most infuriating things that people say, I can't believe that mold can create that problem. Well, educate yourself a little bit, read peer-reviewed studies, and there's no scientific evidence that mycotoxins do not cause neuroinflammation. They they do. And it just boggles my mind that people will say, well, I don't believe that. It's like, okay, all right. Um, so the so the somebody just said, what's the name of the dust mold test? ERMI, E-R-M-I, E-R-M-I. So particularly if you're living in an older home, or if there's been water intrusion, and it can be hiding in so many different places. It's absolutely astonishing. So if you got the mycotoxins down, here we go. Now, lead. I remember last year I was at the AAEM Environmental Health Conference, and one of the speakers said, everybody in this room has some lead in them. Because we used to put lead in the gas, we used to put lead in our paints, and it's now in the soil. It's just about everywhere. So remember I talked to you earlier about the importance of the heme cycle. I won't read that again because I told you before. The enzyme ALAD, which is a really important one, uses zinc as the cofactor. Remember I said an enzyme takes a cofactor and goes along. When you've got this genetic mutation right here, this one that ends in 13, and 72% of them had it, lead goes in rather than zinc. And this whole thing does not work as well as it should. I mean, this number blew me away. 64% had heterozygous, 8% homozygous, 72% had one or the other. So if they're exposed to any lead, there's a problem. Um, so somebody just said, what can we do to keep water damage out of a property? Yeah, that's a little out of my scope, but you really have to work with people, contractors and things who can take care of that for you. Um, but if you've had water intrusion, there's a very, very good chance there's mold. And if you don't get a child out of mold, there's not much you can do to help them. Now, this is going to be a topic I'm going to go about just later when I give you that sneak preview of glutamate. But there's a substance called ALA, and it's not alpha lipoic acid. It's a long name. I'll show you later. But if this doesn't get converted, it blocks the GABA receptor sites. And that very, very high glutamate, because the GABA receptor is blocked, is what makes these kids their autistic characteristics, the high glutamate. So in my opinion, we need to be looking at, does my child have a mutation on 5313? Because if you do, then you need to do a little testing on lead, and you may have to do a little bit of chelation. But other than that, you need to support this process along, particularly if the child gets hangry. They get agitated, worried, fearful, and they want food, and then they calm down after food. That's a typical characteristic of this. So if we don't have the heme, look what happens. We don't make biliverdin and bilirubin, and bilirubin calms down. Now, I know this is very complex, but this is the guy that gets stimulated by all those environmental factors. So remember that list of environmental factors that we draw here, that long list of environmental factors I gave you, that the environmental factors that stimulate this, well, bilirubin calms it down, but it's dependent upon heme and also some genes called hemox. And hemox also calms down mast cells, which can be a problem as well. So that's why this heme is so important for two things. If you remember, I talked to you about how the CBS enzyme needs it. Okay. And then also the cytochrome P450 is needed. And so if we don't have that cytochrome P450, that's what makes your bile. So if you've got all that going on, you're in a boatload of trouble. Okay. All right. Now, the other thing that can happen is EMF, glyphosate, homocysteine, arsenic will also stimulate NF-kappa B, through what's called the NMDA receptor. So that's why it's so important to make sure, like we do a measurement of glyphosate. And then there's also this guy, if we're exposed to electromagnetic fields, this will cause this, and that's why we're seeing more and more people with EMF sensitivity. So it's a serious, serious problem. The Now, the next thing is we're going to look at NLRP3, and we're going to look at what the problem becomes here. So here's your NLRP3, and again, don't worry if you get lost in the biochemistry. We're just explaining what happens. But look at this list up here: stress, hydrogen peroxide, homocysteine, Lyme disease, infection. The main things that drive it is calcium influx, potassium efflux, forest fires, mast cells, lectins, microplastics, aluminum, high ammonia, glyphosate, mold, oxalates, cholesterol crystals, lead, excess glutamate, and peroxynitrite all stimulate this guy. And if you remember, that's what causes the interleukin 18, the interleukin 1 beta that create the problem. Did we just lose sharing? No. No, we're okay? All right. I just saw something change on the. We're still seeing the slides? Yep, okay. All right, just something switched on the
That
view
was
that I'm.
me. Sorry.
Oh, no, no worries. Just so we're okay. So all of these things will impact this NLRP3 to be overactive. So you can see why all of these environmental factors that we weren't exposed to before are now stimulating the NLRP3. All right, now the next thing. There's something called tick SNPs. There's an enzyme called TXN. So when we don't have low inflammation, this tick SNP is bound to it. When we get a lot of inflammation, it is released and stimulates NLRP3. And look who the culprit, well, one of the culprits is high fructose corn syrup. Again, I was born on a different planet where we didn't have this stuff. It only came around in 1968, 1969. Okay. So combining all these together, the high fructose corn syrup will cause this guy to break loose and stimulate the inflammasomes. Okay. All right. Then what happens when this thing gets upregulated? And now this is probably one of my more important slides. So as the NF-kappa B does its job, as the NF-kappa B comes down through here, stimulates the inflammasomes, it stimulates that interleukin 18 that we spoke about, and here comes mast cells and histamine. And we can have genetic issues on histidine decarboxylase. We can have genetic issues that we don't make enough DAO. We can have genetic issues that we get stuck in here. And I'm not going to read all these numbers, but then you get a feedback loop here going on. Then through interleukin 1 beta, you make glutamate, and that comes around, and you're going in one big circle. And if I had to summarize what I'm talking about today, that's it. And then, again, I'm not going to read these for sake of time's sake, but the genes that break down the histamine, the genes that make more histamine, the genes that make more glutamate, they're highly more motivated in all these kids. And here we go, folks. Here's what happens. We're on one merry-go-round here of histamine and glutamate. Well, okay. So that's what occurs. Now, what inhibits this? Well, we spoke earlier about hydrogen sulfide. Very important that you make sure you have adequate hydrogen sulfide. That's why knowing if you have SNPs on the CBS are so important. Nitric oxide, NRF2, we spoke about that earlier. Deacetylation by the SIRT2s. And we're not going to get into ADH5, but that's another one that will stop something called peroxynitrite from stimulating it. So as you can see, there's multiple factors. And what we're working on in our software that we created, we want to try to put artificial intelligence to this eventually so we can sort all this out, because obviously it's mind-boggling. So many, but I'm just trying to illustrate how many pieces come together with this. Okay. All right, now, a little bit on the sirtuins. I talked about those earlier. So sirtuins, if you do a little research and you search for sirtuins longevity, you will find that the sirtuins are related to longevity. And that's just not for autistic, for anybody. And one of the more important ones is called SIRT1. And look at what SIRT1 does. SIRT1 helps you with your neurotransmitters, the master antioxidants, the vitamin D receptors, the FOXOs that help make antioxidants. Then all these guys are pro-inflammatory, and SIRT1 knocks them all down. So what they do, as I told you earlier, they need NAD. Okay. We need NAD. We need the SIRT1 enzyme. So you can have mutations on SIRT1. I'll show you later how you can have trouble here. And that's how you help the good guys slow down the bad guys. Now, Bob Miller clinical observation. When people have a homozygous on SIRT1, whether it's autism or just general health, these people are really, really struggling. Okay. So then here's that chart that I showed you earlier, and you can see here that SIRT1 holds back that NF-kappa B. Okay. SIRT2 holds back the NLRP3, and SIRT3 holds back an enzyme that takes glutamate. I'm sorry, supports the enzyme that takes glutamate and turns it into alpha ketoglutarate, so it's not excitatory to the brain. So you can see this is a 3D chess game. We need the SIRTs working well. We need NAD, and we need to be able to recycle our NAD as well. So multiple factors coming together here. All right, now the critical NAD, that stands for nicotinamide adenine dinucleotide. I'm sure most of you have heard of it. And what it does, it accepts electrons, it donates, and then it turns into NADH that donates electrons, and it fuels those SIRTs. But it also recycles your glutathione. It's needed for fatty acid synthesis, cholesterol synthesis, and nitric oxide production. And it also suppresses that NF-kappa B and NLRP3. Low NAD promotes chronic inflammation and mitochondrial dysfunction. Now, there's also a ratio, and I'm going to show you that in a minute. I'll actually show you that in some of the kids here. So if you've got a high NAD-NADH ratio, everything's good. If this ratio is low, it's bad. So here is how we make it. Now, again, I'm not going to get too deep into the woods, but here's the enzymes that make it. So here's your dietary niacin, comes down through here and makes NAD. Then it makes NADH that makes the ATP in the electron transport chain. Now, one of the things that people have a hard time believing is we say many of these children are low in ATP energy, and they're like, no, 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 they're bouncing over the walls. They've got all kinds of energy. But that's not the good energy that they need. And here's NQO1. NQO1 takes NADH back here. And if this is not working, we've got some problems. Here's your SIRTs that we talked about. And then also we need to, we have a recycling after we use the NAD, we have to recycle it. And you can have genetic mutations anywhere along there. And you have to look at all of that. It's complex. Now, this is interesting. This is the pathway of just making NAD. Each of these, greens is one of the enzymes. 94% of the 36 participants had at least one SNP in the NAD production pathway. In other words, they weren't making enough of this. Now, this may be one of the more important slides as well. Remember, I told you very early on, NQO1 is really important. I believe every autistic child needs to know what their NQO1 status is. Now, the reason that's so important, the reason that's so critical is because this NAD comes over here to NADH, and that's what donates the electrons for what's called the electron transport chain. Okay. But if we have too many of these, interestingly, we make superoxide rather than ATP. And then also this NQO1 controls CoQ10. Remember, you learned that early on. And CoQ10 is what helps these electrons go down through here. So if we don't have enough CoQ10 being oxidized or reduced, or too many electrons here, we're inflammatory. So if you look here, 81% have an NQO1 or KEAP1 SNP. 53% have just one of the two. 28% have both. So I believe this is a key in autism, NQO1. And when you have one SNP, it's not working as well as it should. But when both parents give a mutation on NQO1, this is the elephant in the room. Now, is this the elephant in the room for every autistic child? No, as you can see, there's many others, but this is one of them. Okay. Now, the next thing here, now this is probably one of our more important slides. If we don't have this NADH coming back because of NQO1, this illustrates a little bit more effectively what I just said, that the electron, rather than coming down to ATP, turns into superoxide, a free radical. By the way, if you're intrigued by superoxide, you just go on YouTube, type in Jill Carnahan superoxide. Dr. Carnahan and I geek out for about an hour and a half on superoxide. You might want to put that in the notes. Then if we have superoxide, we need something called superoxide dismutase to turn it into hydrogen peroxide. Well, if we don't do that, we get DNA strand breaks. Well, there's part of your autism, DNA strand breaks. However, if we even do this, if we turn hydrogen peroxide, I don't have it drawn in here, there's 3 other enzymes that I'm going to talk about later that turn this into water and oxygen. If we don't have that, we make hydroxyl radicals that does your DNA strand breaks. Now, to think we made this complicated, let's just complicate it a little bit more. There's an enzyme called PARP that repairs your DNA strand breaks, but guess who they depend upon? NAD. So if you don't have enough NAD because it's being sucked over here, you're going to make superoxide, you're going to do DNA strand breaks, and you're not going to be able to do the repair. So this could be yet another mechanism. Now, here again, we're just going to show you why that NADPH is needed. So that NADPH that needs to be made by that cycle is what takes your oxidized glutathione back to reduced. And NADPH makes nitric oxide, helps with your fatty acid synthesis, powers your phase 1 detox, and is part of your cholesterol synthesis. Isn't that interesting? All of that's from NADPH, which, as you can see here, is made from NAD. So here's your NAD, here's your NADP plus, here's your NADPH. That's how it recycles your antioxidants, plus does all this other really important stuff too. Now, if someone is of Southern Italian or Native American, they many times have mutations on G6PD. It appears though the 36 kids we had were not in that category, so we didn't see that. But African Americans, Sicilians, Native American Indians, and South Americans often have a G6PD that also impacts the production of NADPH. So if you don't have enough NADPH, you're not going to recycle your antioxidants. Now, this is probably one of the most significant things we've come across. So if you're glazed over by now with all this information, do try to pay attention to this one, because this is, I believe, the smoking gun. So we already made an argument of NAD is needed to make energy. It's needed to make NADPH. It's needed for the sirtuins. It's needed for the PARP. But interestingly, NAD can be used to make inflammation. Isn't that fascinating? Okay. So back to our environmental toxins. Oh boy, here we go. This is not the full list, but mycotoxins, Lyme disease, aluminum, EMF, high fructose corn syrup, lead, mercury, nickel, glyphosate, they will stimulate NF-kappa B. Remember, you learned that early on. Now, here's the new piece of information. It stimulates something called CD38 that consumes, hang on to your hat, friends, 100 molecules of NAD to make something called cyclic ADP ribose. And what does that do? Hang on to your hat. Stimulates the inflammasomes, makes the gasdermins, starts rupturing your cell membranes. This discovery, I believe, is one of the keys to why we're seeing so much autism. Because these environmental factors are taking this precious NAD and just sucking it down into inflammation. And then these are the not only autistic kids, but people who do NAD. You know, NADs, if you just look at some of the health influencers, they talk about NAD, look at all the good stuff it does, woohoo. Go get an intravenous injection of NAD, infusion rather. For some people, it's like, this is the best thing I've ever done. And other people, have made them so sick, it took them months to recover. The reason being, if you take an infusion of NAD and this guy's running to beat the band, you've just fed the fire. So one of the things that we're really spending a lot of time on right now is there's a company called US Biotech that we use to measure your NAD levels. And if this CD38 is running too fast, NAD actually works against you. So we made a product called NAD plus NADPH Assist that helps NADH come over here. Plus, it's got luteolin and quercetin to calm down CD38. And that's why those nutrients can sometimes be so helpful. So apigenin, luteolin, and those help calm down CD38. So your strategy has to be, firstly, try to get rid of this stuff, calm down NF-kappa B, boost SIRT1, calm down NF-kappa B, calm down CD38, then give the NAD. You have to do it in the right order, folks. So don't go away from this saying, oh, let me go get some NAD and see how that works. It very easily can backfire very quickly. So the product that we have with NADH, or the nicotinamide riboside in it, 8.5 milligrams, fairy dust. But then you'll see here it says Paudiarco. Paudiarco helps take it this way. And then luteolin and quercetin calm down this guy. And then also parsley does as well. So this product contains all three things to calm this down over here, and 8.5 milligrams of NAD. Aside from autism, we just had a lady that was in a wheelchair, 40-some years old, sick from Lyme and mold. She's now walking because we started supporting this. So this may be one of the most important things we've talked about. And again, it comes back to the environmental toxins. And again, you know, when you get vaccinations, you know, there's oftentimes aluminum in there. These kids are with their cell phones all day. They're eating high fructose corn syrup. The cereals they're eating have glyphosate in them. Uh, they're living in a mold home that's moldy. All of that together, the proverbial perfect storm, environmental factors, upregulated NF-kappa B, weakened SIRT1, less than optimal NAD, kaboom, NLRP3 and inflammasomes. All right, so intracellular NAD depletion. Here's a paper that says NAD depletion provides a non-transcriptional priming signal associated with mitochondrial dysfunction. Now, we're getting down to the end, and then I'm going to just stick my toe in the water with leucovorin, and so stick with me. I want to talk about leucovorin and acetaminophen. So again, you're probably getting a little overwhelmed with biochemistry, but just very briefly, when that NOx enzyme gets upregulated from NF-kappa B, it will create hydrogen peroxide. Yep, that's the same thing you can put on cuts. And hydrogen peroxide needs to be cleared by glutathione, thioredoxin, and catalase. And if not, it makes hydroxyl radicals that will once again do DNA strand breaks. And remember, you need PARP to hold that back. It'll do something called lipid peroxidation that starts poking holes in your cell membranes. I'm not going to read these numbers because it's probably glossing over, but you can, watch the video, pause it if you want, and you can see in this study how many of them had weakness here as well. So here's another way the cell membranes are going to get damaged. Okay. So and then finally, we look, these are just numbers on how they have weakness here. And there's an enzyme called PON1 that starts repairing, but that's impacted by glyphosate. All right, final step, we have to do repair. And we're just starting to get into this. This is part of our newest research. There's something called the escorts and autophagy. So we're just putting this here. This is part of our future research. How do we repair these cell membranes when they get damaged? So I just put this here as part of our future research. Now you'll find this interesting. This shows the participants. I just showed 4 of them of the 36. And these are all the things these are all the enzymes that we spoke about. And you can see here participant number 17, 12-year-old male, had 27 of the 38 things we look at here. 14-year-old female, 30 out of 38. Participant number 8, 23 out of 38. Participant number 1, 30 out of 38. So you can see how these kids just really have this high predisposition for this to occur. So these are all the things we spoke about. And you can see that the majority of them have most of the things that we spoke about, leading to that perfect storm. I'm not going to read these, but these are the SNPs we believe that you need to measure and compensate for. Again, you can look at the slides, and Tracy, if you want, we can give you a PDF of the slides if you want to attach that. These are the ones that we need to be anti-inflammatory. These are the ones that build and repair. And so what we think we need to do, 10-step plan of action. Notice I put number 1, look for mycotoxins. Can't emphasize how making sure there's no mycotoxins. And please don't say, I don't see any mold, so it can't be a problem. Trust me on that one. Just because you don't see it growing on the wall doesn't mean you don't have it.
Can I add a little 2 cents on this one?
Sure.
Okay, so being married to somebody who was once a restoration contractor, and we also owned our own environmental testing company. And then I did environmental work when I was in the Air Force. So I know a lot about this because somebody had asked a question about how do you know if there's mold? So I have a house that's only 7 years old and there was still mold in it. And you can have an environmental testing company come in and actually, put up air sampling monitors. They can do, like he said earlier, swab testing. But also, if there's been a leak, if it was not properly remediated, and when I say remediated, I mean gutted, cleaned, and I also use the word proper. If somebody came in and just gutted the stuff out and didn't tape and contaminate, and can, control that area and tape off that area, mold spores pick up and they move and they land somewhere else and then they start to grow. So making sure that somebody is properly remediating it, if they're taping off the area that they're gutting, and getting all of it and then following it up with testing is the best way to make sure that you get that stuff out of your home. Because even the newest homes, if you have moisture in your home, if you live close to a beach, whatever, there's a huge possibility that if there's a lot of moisture in the air and it gets into your home, it gets into your vents, then you can have mold contamination. Getting certain air filters, air scrubbers in your home to get that stuff out, but properly remediating that and making sure that it was done the right way. And you can always send me an email if you have any further questions, because my husband has done this for over 35 years, to make sure, because it's, you think that you don't have mold, most of us have mold in our bodies, and I'm one of those, so.
Yes, well, thank you for that, Tracy. And what happens is two people can live in the same household. One person is sick and the other one says, but I don't feel anything. So that's where the genetics comes into line. So the one person, and then many times I've had, not so much with autistic children, with husband and wives, major disagreement where the wife says, I'm sensitive to mold, and the husband says, you're just a hypochondriac. And it's come as a real problem for some folks. So then support the phospholipid bilayer. If your NF-kappa B is upregulated, you better start calming that down. There's a couple herbs that do that. We've actually made a product called Peroxablocks that does that. Use the genetic findings, and I'm going to give information on the genetics because people are asking about that, to identify and find the triggers to NLRP3. Use supplementation to slow NLRP3. There's actually nutrients that will slow them down. Use genetic findings in labs to support glutamate to GABA. Use genetic findings to find potential weakness in the sirtuins. Use genetics in labs to look at the NAD, NADPH. I thought I had a slide here on how we measured that, but I guess I didn't include that here. US Biotech does a measurement of that. And then see if there's the creation of hydroxyl radicals that create the lipid peroxidation and DNA strand breaks, and support autophagy if needed for cell membrane. So just a quick advertisement here. We have our own genetic test called your functional genomics. Gets sent to you. We extract the DNA. We run it through our software. We do a consultation and then put together a protocol. For children, we often make powders. So we can custom make a powder that you can just mix in with something, put a little sugar with it, and pretty easy to do. So swab or saliva, the cost of the test is $315. Here's who we are, the Nutrigenic Research Institute. That's the software that does the analysis. That's the saliva test. That's the nutrients. And if somebody wants to get a hold of us, here's our website, tolhealth.com. Sorry, that should be an M. You all know that. Here's our phone number, 717-733-2003. If you go to the website, you can fill out an application. You don't even have to call us. Then we get back in touch with you about getting the testing. I don't know if anybody on here is a health professional, if there's any doctors on here, but the software that we use, we encourage other doctors to use it. So only if you're a health professional, please. You can actually use the software and then use it for your patients and your clients. So I told you I wanted to give you a quick preview of leucovorin. So folate, and by the way, this is what we're going to be talking about in depth at your spring conference. So this is just teaser. So this would be a teaser why you want to attend and hear the whole lecture. So we need folate. Oops, what did I just do there? Hello. Oh my. Hang on. Hang on. There we go. So we need folate in the brain. So if we don't have folate in the brain, we're going to have a lot of problems. So what happened is, many, many years ago, we had our own gardens or we bought food from the farmers and we got plenty of folate. Well, then as we started processing foods, the food industry took out the folate in the foods. And that's when many years ago we started getting birth defects like spina bifida, infertility, or miscarriage, because we need folate for a process called mTOR, which is the growth of new cells. That's why women need folate supplementation when they want to get pregnant. So the food industry, in all their wisdom, decided, oh, well, we're just going to make our own folate, and they made something called folic acid. Folic acid is artificial. It doesn't exist in nature. It's man-made. Now, for some people, that's just fine. However, here we go back to the genetics, okay? There's a genetic mutation on an enzyme called DHFR, and I'm going to circle it over here. Let me get the drawing tool. This one right here, you can see this on the right. Now, this is coming from the software. This is one of the kids that participated in the study. And you see there's a down arrow right there, and there's a 1. And what this one does it doesn't allow folic acid to pass through as effectively. So if you've got this genetic mutation right here, either a 1 or a 2, folic acid doesn't come down through here. And then you get what's called unmetabolized folic acid. And when you got unmetabolized folic acid, that creates a problem. Now, the big interest is in leucovorin, and interestingly, leucovorin is nothing more than folinic acid. They just have a large amount of it and a couple of things with it. So it's really nothing special other than it's a lot of folinic acid. So look what folinic acid does. It bypasses DHFR. So that's why there's so much interest in folinic acid. So in my opinion, before you go down that route, you want to know if DHFR is a problem. If this isn't a problem and you don't have MTHFR, leucovorin might be okay, but it isn't the solution you're looking for. So we're going to be generating probably over the next couple of months, a genetic report specifically for identifying if this is an issue. So everybody's heard about MTHFR. Way too much attention has been given to it, but it's what puts a methyl group on here. And I can't tell you how many people have learned about MTHFR. They give their kid methylfolate, and it's a disaster because it creates too much inflammation. Then you can see on this guy right here, we're just digging into this ABCC3. This helps move methylfolate from the liver into the bloodstream. And by the way, this is dependent upon ATP. So all these ABCs are dependent upon ATP. So if you don't have enough ATP because of that NADH problem, this isn't going to work. And then here's where your folate gets to the brain. Now, acetaminophen. So this is a map in progress, but we're working on it. And again, this is a map made for each child. So here's your acetaminophen. And when it does its job, it has to be cleared by a process called glucuronidation. And you can see this child who's part of the study. This 2 over here means his glucuronidation isn't working very well. Okay. Then sulfation isn't working very well. So then I'm sure you've all seen this, how it makes this NAPQ1 or QI that is very toxic to the liver. And everybody's talking about, well, it depletes, you need your glutathione to do that. But I think that's part of the equation. We're beginning to work under the premise that we believe it's NADPH depletion because the NADPH is the cofactor for your glutathione. Now, look what aluminum does. Here comes aluminum. It makes more superoxide using your NADPH. So there goes your NADPH. It inhibits SOD2 that takes care of superoxide. It inhibits glutathione peroxidase 1 and inhibits the GSR enzyme that recycles your glutathione. So talk about a perfect storm. Kid gets a vaccine. And again, we're not anti-vaccine here, but we're saying if you get too much aluminum, too fast, and then you have genetic predispositions here, and then you're told, oh, you got a fever, take Tylenol. Perfect storm of creating all this inflammation, further depleting your glutathione. So this is purely hypothesis at this point, but we believe that the NADPH is the big player, which comes from your NAD. Okay, next preview, and I think this is what's going on. Remember I told you that we have glutamate and we have GABA. So glutamate's what makes you intelligent, highly motivated, go-getter. And that's why many of these kids are like geniuses underneath. They're brilliant, but it's going so fast they can't function. So there's something called GABA, and glutamate needs to turn into GABA. Well, you can see on this young man here, when we look at his genetic report, he's not turning his glutamate into GABA. Then there's something called a GABA receptor site, and I believe we're the first ones to talk about this. When the GABA attaches to the GABA receptor site, an enzyme called NKCC1 takes chloride into the cell. Then KCC2 takes chloride out of the cell. If these are out of balance, it all breaks loose. High glutamate, high inflammation. And look who we have here. Lipopolysaccharides, glyphosate, organophosphates, mercury, lead, cadmium, and aluminum can alter the redox balance, increase the reactive oxygen species that phosphorylate and inactivate KCC2. I have a sneaking suspicion this is the bottom line of what's happening to these kids. And not only these kids, people that are addicted to the benzos, people that have ADD, ADHD, anxious as can be, this is out of balance. Now, look at this young man here. Tumor necrosis factor is overactive. You see there's an up arrow there and a 1. That suppresses KCC2. SIRT1 suppresses something that suppresses, so SIRT1 actually helps KCC2. And this enzyme right here, this one that you see over on the right here, that's inhibiting the encoding of this. Now we're going to do further research on this with those 36 kids. We're just starting it. We want to see how many of them have an upregulation of TNFA, a downregulation of SIRT1, upregulation here. And that's what we'll be presenting at your spring conference, Tracy. We're going to be showing why we believe this is one of the primary things that's out of balance. And there's a lot of thoughts we got to connect. This chart is going to get gigantically bigger as we look at phosphorylation and many other factors, early stages. But I just wanted to give a teaser why somebody should come to the spring conference, because we're going to be delving into this in depth. And if all goes well, we'll have computer programs that can figure this out for you as to what to adjust. So I apologize if your head is spinning or if you just said, I just can't follow this. But the bottom line is there's many environmental factors, genetic factors that cause the neuroinflammation, and therein lies the problem. So there again is our contact information, tolhealth.com, not con, obviously. There's our phone number. There's a form you can fill out there if you want. $315 for the test, $199 for the consult. And again, if you're a health professional and it's like, whoa, I got to do this, contact Yvonne Lucchese or Chrissy Bannon. There's our phone number. There's their email addresses, and they can get you set up to do this so you can help the kids out. So I know that was a boatload of data. And
So
I
we
hope
have a
I go
few
on with them.
questions.
Okay,
if you're up
sure.
for it. So Krista, she has an ASD son with methylation issues. She said, can you elaborate on iron, vitamin D, and folate deficiencies that can affect bilirubin levels and what can be done to treat it?
That's a lot. Okay.
I know.
Um,
That's
well, firstly, can you repeat the question?
okay. So, young man, because I think he's in his early 20s, as I know, with he does have MTHFR. I know that because I know Krista. Can you elaborate on iron, vitamin D, and folate deficiencies that can affect bilirubin levels?
Sure. Okay. Well, if you remember, if you go back, maybe watch the replay, we talked about that we need the bilirubin to work for and you need that heme cycle to work properly. So if that heme cycle is not working properly, you're not going to have enough bilirubin to hold it down. I remember we said the vitamin D is needed to make sure the iron gets transported out of the cell into the bloodstream. And I personally believe we've put way too much emphasis on MTHFR. It just seems like the whole world revolves around MTHFR. And yes, but 50% of the population has it. So I don't think it's as important as we've made it seem. And you can go on Facebook, and there's people that are somewhere a combination between a used car salesman and a televangelist who tell you that, look at your MTHFR, your COMT, and your PMT, and all your problems are solved. And I think that's just not true. And so MTHFR just means that you might have a difficult time putting a methyl group on your folate, but many times people see that, they take methylfolate and they get worse. So you have to do that very carefully, and that's where folinic may come in. And so MTHFR is important, but I don't think you should freak out if you have it, or immediately start taking methylfolate because you do.
All righty. Can you talk about supplementing with GABA to help bring balance to glutamate?
Yeah, that's an interesting question. The and I used to think that myself, that, well, if you have trouble with GABA, then just take GABA. But I've talked to so many people over the years that said they got worse on GABA. Two theories on that. So this in $3 will get you a cup of coffee. Okay, just hypothesis. Okay. So if you have too much glutamate, what you need to do is you need to support the glutamate to GABA conversion. That's why we use things like magnolia bark to support the glutamate to GABA conversion rather than giving GABA. And it was just recently as we found that when the GABA attaches to the cell receptor site, if the GABA is actually, it's called the GABA switch, where GABA, rather than being inhibitory, is actually excitatory. And that just blew us away. So GABA that we think is our friend, if that chloride balances out, GABA is actually excitatory. And that's what makes this so infuriatingly complex. So that's why sometimes GABA is fine. Sometimes that's why GABA backfires on us.
Typing. And I couldn't get out that, but can GABA actually turn into glutamate?
No, not to my knowledge. I don't think it goes backwards. But again, if you take too much GABA, the conversion, again, this is hypothesis, not a fact, the conversion of glutamate to GABA may slow down and increase your glutamate because you're not turning it. So again, that's why we're big fans of magnolia bark, sometimes called hinokial, that supports that conversion rather than just giving GABA.
Um, how can one increase GABA?
Well, as I said, if you've got mutations in the GAD gene, there's a GAD1 and GAD2. We actually created a product called Excitoblocks Clarity that, again, back to that same nutrient, magnolia bark, uh, or sometimes called hinokial, actually supports the glutamate to GABA conversion. Now, if somebody's got low glutamate and low GABA, taking GABA is going to be helpful. But I think what we're finding in the autistic kids, they've got high glutamate, and giving them GABA actually can be contraindicated. Now, is somebody going to say, I gave my kid GABA and they were better? Sure. But I think for the most part, we have to be very careful that it's the conversion of glutamate to GABA and also making sure that that chloride channel is not off, because it blew us away when we learned that GABA can actually be excitatory rather than inhibitory. I mean, that's mind-boggling, because all you've ever heard over the years is GABA is the don't worry, relax, be happy. But when that chloride gets off, it actually becomes inflammatory. Mind-boggling.
Use my typing skills, everyone. Where do we get genetic testing that would give us the information? Don't you have that on your website, Toll Health?
Yeah, yeah, yeah. We can put that
Yeah, I
down.
put it in the comments section, all his websites and
Yeah,
some.
yeah. There it is. There's our website, tolhealth.com. You can go there and you can fill out the form or just give us a call. And it takes about 11 or 12 weeks to get the test done. And then we set up as if somebody's local, we see them in person. But most of the folks are out of we talk to people all over the world. So then we just do a Zoom call, just like we're doing here, do a screen share, show you what to do. So,
Um, somebody said Apigenin and what?
oh, apigenin, uh, luteolin
Okay.
will calm down the CD38.
Okay, if I spelled this wrong, I apologize. Oh, she had gotten it because she put it in the next comment. Is there a list of the ideal tests for us to identify these genetic and pathway variables?
Well, I mean, of course, we have a bias, and it's our own test because we spent years developing it. So it's called Your Genomic Resource. So we actually worked with Thermo Fisher, and we said these are the SNPs that we want, and we measure the chip has 220,000 on. I believe we look at around 80,000 of them. And that said, we were very fortunate. I have a good staff. My son, who has these masters in genetics, is kind of the one who's the brains behind identifying which ones are the evidence-based, because just because you have a SNP, that doesn't mean it's actionable. So you have to look at the literature like ClinVar and find out which are actionable. So we have our own genetic test. I mean, there's others out there that'll measure it, but as I said, you get the genetic test done, you run it through the software, then you get the reports and the consult. So that's how it works.
So once they do this, does this provide guidance for you to create a treatment plan?
Uh, yeah, that's what we do. In other words, we go through and find out where the weakness is, and then you start putting the treatment plan together, and you have to go slowly because a lot of times if you try to do too many things, you get what's called the Herxheimer reaction. So then if you get the Herxheimer reaction, so many times we say, let's start out on this, then we'll check back in a couple of weeks, 7 to 8 weeks, see how you're doing, then do the next thing, then do the next thing. Because if you've got multiple issues going on at the same time, you can't attack all of them, or you get that Herxheimer reaction. And I'm sure many of these people have tried things and it backfired horribly. So we try not to let there be a backfiring.
Okay, Catherine says, I have had genetic testing for the methylation cycle completed for my son, and he has significant issues in MTR, MTRR, and MAOA, among
Mm-hmm.
other less severe SNPs. We supplement accordingly, and I am wondering if this can be taken into account in your genetic test. It seems like you are looking at a lot more pathways.
Yeah, a lot more. Yeah. I mean, we do look at all of those I mentioned. We look at those. And as we said, unfortunately, there's some folks out there that say this is the answer to everything. And unfortunately, it's not. It's complex. So we have I don't think I'll pull it up now, but we have that whole thing mapped out. Everything she said there, we have that in a map and can look at. But that's just one of the many, many things we need to look at. It would be nice if life was so simple that took care of it all, but unfortunately, it's a little more complex than that.
Is the test that you run in genetic testing the same?
Yeah, I mean, the test we do is a genetic test. You do a swab or saliva. You send it to the company, pulls out the data. It's our own proprietary genetic test. In other words, we're functional genomics. People say, do I have the things for breast cancer? Do I have the dementia? It's like, we don't measure that. We're not geneticists who look at, disease related. We're looking at function. So there's a different, like you can do 23andMe and Ancestry. They look at your ancestry, which is pretty cool. We don't do that. We don't look at the weird disease stuff. We look at how are you breaking down your fats? How are you recycling your glutathione? How are you handling your iron? Nothing that's specifically disease related, but all the things that combine together to make this inflammatory storm.
Okay, last question. Is a swab enough of a sample? My son could not spit to collect saliva sample from
Yeah,
testing.
well, you have a saliva swab where you just get some cells from the cheek.
Okay, I lied. That wasn't the last question. I have a couple more.
Okay.
If the chloride channel is off and is creating issues with GABA being excitatory, what would you suggest?
Well, it all depends what's causing it. So if it's the TNFA that's upregulated, you got to calm down TNFA. If it's the SIRT1, you've got to work with the SIRT1. If it's because the something else is causing the reactive oxygen species, then you got to work on that. So there isn't a formula for that. It's got to be personalized. Now, having said that, we may make a formula that just covers all of the bases a little bit, but that's still preliminarily. But once again, there isn't a one size fits all here. It's complex, unfortunately.
So on your website, there's a DNA saliva test kit.
Hmm.
Click on new client form, and there is a link to functionalgenomicanalysis.com.
Hmm.
Same thing?
Hmm. Yes. Hmm.
Yes. Okay.
I
Okay.
just
And
want to say thank you so much for that college level crash course. Robert, we're so grateful for you taking the time to do this research. Really incredible. Thank you.
Well, my pleasure. It's again, it's a team effort. It's my son, Dr. Landis, Dr. Kelly, Yvonne Lucchese. Um, we're all very passionate about this because I mean, my heart goes out to these kids. They should be having the time of their life, and here they are, sometimes banging their head against the wall. The parents are like in a war zone trying to deal with it all, and it's just so unfair. So that's what motivates us to try to crack this code. So we work from morning till night to try to figure this stuff out. So and as I said, it's not easy. If somebody says they have found the answer, I would be very concerned it's not. There's many ways to the top of the mountain, and unfortunately, many things we have to unravel. But if we all get our heads together and work very hard on it, hopefully we'll be able to crack this code. But it's not going to be easy. It's not going to be fast.
All right, so real quick, I just want to share this slide one more time. Again, we are a nonprofit organization and we do heavily depend on donations. Even if you could make the smallest reoccurring donation each month, if it was $5, $10, $25, whatever it is that you would like to donate. It keeps our organization going. Upcoming next month in November, we're going to start our parent group. We are also going to be doing a silent online auction. So we have some pretty exciting auction items. We have, custom signed baseball bats from Robert F. Kennedy Jr. and General Flynn, and some other great items. And then in December, we are going to be starting up our Giving Tuesday campaign. So however it is that you can join in and support us, that would be great. If you would like to purchase tickets for our upcoming conference, April 24th through 26th in San Diego at the Legacy Center, go to autismhealth.com. This year's discount, or this month's discount code is Spooky25, and it does end on the 31st. And prices will go up January 1st. Our prices are a lot more affordable than most conferences out there. It is a nonprofit organization and we take donations so we can make it affordable for families and parents and practitioners to attend. So I don't have to charge twice as much. So we appreciate, sponsors like Robert Miller. Robert Miller is one of our sponsors for our conference, and I'm truly grateful for his time and consideration, and for doing today's webinar. Thank you, Bob.
My pleasure. It was a lot of fun.
So I hope you all have a beautiful weekend. Enjoy your Saturday. And if you have any questions or further questions that you would like to ask, you can send them to info@autismhealth.com, and I will get those over to Bob and he will get me the answers. And, I hope you have a beautiful day. God bless everyone. Thank you again for attending.
All right. Bye-bye, everybody.
Bye-bye.